Welcome to a presentation on the properties of exponents. The goal of this video is to use the properties of exponents to simplify expressions. Here is a list of the properties of exponents we will be discussing today. You may want to pause the video now and write these down. We will consider them one at a time. The first property is the product property. It states that if you're multiplying and the bases are the same, you add the exponents. Let's take a look at why that makes sense. If we want to multiply 5 to the second times 5 to the fourth, we know that 5 to the second means 5 times 5, and we know that 5 to the fourth would be 4 factors of 5. And so now we can just count the total factors of 5 and we can see we're going to have 6 factors of 5. Well, if we take advantage of the product rule, that states that we can just take the exponents 2 and 4 and add them to get 5 to the 6th. Now this is obviously much shorter, but if you're not sure of a rule, it's always best to expand the exponents to find the product. Here we have x to the 6th times x. Well, the first thing we have to recognize is that when we have x and there's no exponent listed, that means the exponent will be 1. And that's actually one of the properties listed on the previous screen. So if we have x to the 6th times x to the 1st, if we use a product rule, we could just take the exponents and add them to get x to the 7th. Hopefully that's logical, because we know if we expand x to the 6th, we'd have 6 factors of x times an additional factor of x, which of course would give us a total of 7 factors of x. The quotient rule states that if we're dividing and the bases are the same, we subtract the exponents. So for this first problem, if we have 3 to the 6th divided by 3 to the 4th, let's assume that we could not remember the quotient rule. Again, we would expand each of these, so we'd have 6 factors of 3 in the numerator and 4 factors of 3 in the denominator. And now we can simplify. Every 3 over 3 would simplify to 1, and now we can see we would have 3 to the power of 2, or 3 squared. Well, using the quotient rule, what it's stating is we could have just recognized that the bases were the same and simplified it to 3 to the power of 6 minus 4, which of course gives us 3 to the second. But if we don't understand why this rule works, it's best to expand it and simplify it the long way. So for this next problem, you can see as the exponents get larger, it kind of gets more tedious to write out 15 factors of y and 8 factors of y. So we will just apply the quotient rule by taking the exponent in the numerator and subtracting the exponent from the denominator to obtain our simplified expression of y to the 7th. In this last one, we know that whenever we have something over itself, it is going to equal 1. If we applied the quotient rule to this problem, we would have w to the 4 minus 4 power, or w to the 0 power, which is equal to 1, and this is one of the properties that we saw on the first screen. Anything raised to the 0 power is equal to 1. The power rule states that we have a raised to the power of m, all raised to the power of n. This will equal a to the m times n power. Again, before we apply this, let's take a look at it by expanding this. If we have 3 cubed raised to the 2nd power, as long as we understand what exponents mean, we can expand all of this and we should get the same answer that we would get from the power rule. So if we know if something is squared, that's multiplied by itself 2 times. And now we also know that 2 cubed means 2 times itself 3 times. So there's 2 cubed times another 2 cubed. And now we can just count the factors and we have 2 to the power of 6. Now if we try to apply the power rule, we have a power raised to a power rate multiply. Of course, 2 to the power of 3 times 2, of course, gives us the same answer of 2 to the 6th. So if you ever panic and you forget some of these rules, just expand your exponents and you can still derive them the long way. Looking at our second example, we have m to the 5th power raised to the 4th power. Well, again, the shortcut would be to raise m to the 5 times 4 power, or multiply our exponents, which would give us m to the 20th power. Next we have the product to power rule and also the quotient to power rule. So if we have ab raised to the power of n, that will equal a to the n times b to the n. Now to me, I look at this as just an expansion of the previous rule where we have a power to a power, because this is a to the first and this is b to the first. So if we multiply these exponents, the result would be the same. And the same thing for the quotient to power rule. This is really a to the first and this is b to the first. So I look at this and see we have powers raised to powers, therefore we multiply our exponents. Okay, we have several examples here. The first one we have 7x squared. Well, this is actually 7 to the first and x to the first. So applying this product to power rule, we would have 7 squared times x squared, which equals 49x squared. A common mistake here is that people forget to square the 7 as well as the x. The next problem, I don't see an exponent on the z, so remember that means it's a 1. So here we're going to have x to the 2 times 3 power, that would be x to the 6th, y to the 5 times 3 power, it's 15th power, and then z raised to the 1 times 3 or 3rd power. The next example, again, whenever I don't see an exponent, I always write it in as a 1. So I look at this and I see powers raised to powers, so I would have 2 to the 4th power divided by 3 to the 4th power. And since we can multiply this out, we should. 2 to the 4th would give us 16, and 3 to the 4th would be 81. And the last example here, this would be a to the 3 times 4, or 12th power, and b to the 2 times 4, or b to the 8th power. Now that we've discussed the basic properties of exponents, let's take a look at a couple of problems where we will simplify using several of the properties. So we take a look at this problem. We cannot multiply these two together because 2a squared b is raised to the 3rd power. So we first have to address this outer exponent. This would be 2 to the 3rd power, a to the 2 times 3, or a to the 6th power, and this is b to the 1st, so we'd have b to the 3rd power. Since all of this is being multiplied together, I'm going to rearrange the order. Let's write 3 times 2 cubed times a factor of a times a to the 6th times b to the 4th times b cubed. Again, I'm allowed to do this because this is all connected by multiplication. So now we can multiply this together. 2 to the 3rd would be 8. 8 times 3 would be 24. a to the 1st times a to the 6th would give us a to the 7th since we add our exponents. And b to the 4th times b to the 3rd, b to the 7th. Okay, the last example, we have a fraction inside these parentheses being raised to the 3rd power. Now there's a couple ways to do this problem. We could apply the power rule here, but I did notice that inside the parentheses this fraction can be simplified. Here we have x squared and here we have x to the 1st. So if we applied the quotient rule, we'd have x to the 2 minus 1 power, which would give us x in the numerator, and this is still raised to the 3rd power. So if I lost you there, what happened is we had x to the 2nd in the numerator, and we had 1 factor of x in the denominator. So when we simplified this, we were left with x in the numerator, which is the same thing you would get when you apply the quotient rule, where you have x to the power of 2 minus 1, which would be x to the 1st. Okay, now we can apply the power rule here. So we'd have x to the 1 times 3 power, x to the 3rd, y to the 4 times 3 power, which should be the 12th power, 2 to the 1 times 3, or 2 to the 3rd power, and z to the 1 times 3 would give us z to the 3rd. 2 to the 3rd would simplify to 8. So let's rewrite this one more time. X cubed y to the 12th divided by 8z cubed. Okay, the next video we'll discuss negative exponents. There will be additional examples of these properties in that video as well. Thank you for watching, and I hope you found it helpful.